Welcome to the presentation of the paper on dynamic suffix array with polylogarithmic queries and updates. My name is Dominik Kempa, and this is joint work with Tomasz Kociumaka. For any string t of length n, we define its suffix array SA from 1 to n as an array storing the permutation of numbers from 1 to n, such that t from position SA of I to n is the lexicographically ith smallest suffix of t. In the example on the right, SA of 3 is equal to 5, which means that the third lexicographically smallest suffix of t starts at position 5. Suffix array was introduced by Manber and Meyers in 1993 as a space-efficient alternative to a suffix tree. The key advantage of suffix array over suffix tree is the size. While suffix tree is a pointer-based data structure using O of n log n bits of space with a relatively large constant factor, suffix array is just one array of integers and hence needs exactly n log n bits of space. It is also conceptually very simple. Despite its simplicity, it was quickly realized that a suffix array is sufficient for many applications which previously used a suffix tree, and suffix array quickly became one of the most fundamental and widely used data structures for string processing. Examples of problems in which suffix array is utilized include finding repetitions, for example computing the longest repeated factor or locating all maximal repeats, computing various string properties and statistics, sequence comparison, and data compression. In addition to being utilized in many algorithms, suffix array is also either the component or the first step in the construction of several fundamental data structures. Furthermore, construction of the suffix array is one of the most studied problems in string processing, with around 45 different algorithms existing to date, including external memory, parallel, and distributed implementations. The power of suffix array comes with one caveat. Suppose that we want to maintain suffix array for a dynamically changing text t. More precisely, suppose that we want to support an insertion, deletion, or substitution of a single symbol anywhere in t. The key difficulty in maintaining suffix array under such operations is that it can change in a complex manner even after a single substitution. For an example, consider a text t consisting of n symbols b. Observe that changing the last symbol of t into c reverses the entire suffix array. Even worse, when we substitute the middle character into a, the resulting suffix array is permuted by interleaving the two halves of the suffix array before the update. These updates only permute the suffix array. Insertions and deletions, however, complicate things further, since each can shift a linear number of values in the suffix array by 1. This volatility of suffix array makes it impossible to keep it in plain form while performing updates. This does not, however, rule out the existence of a data structure to compute the suffix array values. In other words, we can still aim to design a data structure that can answer suffix array queries that, given any I between 1 and n, returns the value SA of I. The study of queries on a dynamically changing text is not a new field. Example queries that have been extensively studied in the literature include longest common extension, or LCE queries, that given any two positions I and j, return the length of the longest common prefix of suffixes starting at positions I and j. Substring equality, that given any positions in t and length L, checks if the length L substrings starting at those positions are equal. And finally, pattern matching queries, that given any pattern p, return the set of starting positions of p in t. When studying these problems, we typically aim at a solution that performs updates in text t in polylogarithmic time and queries in either polylogarithmic time or, in the case of pattern matching, in O of n polylog n time. After over 2.5 decades of research, the above complexities have indeed been achieved for all of the above problems. Furthermore, in addition to the basic updates, namely insertions, deletions, and substitutions, many structures for the above problems support more complex updates to text, such as cut-paste operation, which moves any and arbitrarily long substring of t from its original location into any other place in t. Importantly, the runtime for cut-paste is still polylog n and does not depend on the length of the substring being moved. To achieve this, these data structures internally maintain a collection of strings with efficient support for split and concatenation. Let us now review what is known about suffix array queries on a dynamic text. The progress for this problem has been significantly slower than for other queries. In 2010, Salson et al. Described a data structure that performs well in practice, but the worst-case complexity of its updates are linear in n. A decade later, Amir and Bonek described the first structure achieving a non-trivial trade-off. Given any parameter k, their structure supports queries in O of k time up to polylogarithmic factors and substitutions in O of n over k time. This way we can, for example, achieve O of square root of n time for all operations. More recently, they also described a structure able to either perform suffix array queries in polylog n time and updates in O of n to 2 over 3 time, or inverse suffix array queries in polylog n time and substitutions in O of square root of n time. To sum up, prior to this work, there was no solution for dynamic suffix array queries achieving polylogarithmic queries and updates. Not even amortized or in expectation, not even for the simpler case of substitutions only. Thus we ask, can we efficiently support both suffix array queries and text updates? The main result of our paper is the first solution to the dynamic suffix array problem that achieves polylogarithmic time complexity for both suffix array and inverse suffix array queries and all updates, including the insertion, deletion, substitution, as well as the more complex cut-paste operation that, as explained on earlier slides, is currently supported by state-of-the-art structures for other queries. Moreover, our structure is fully deterministic and complexities of all operations are worst case. To achieve this result, we develop several new techniques which are potentially of independent interest. This includes locally sparse string synchronizing sets, dynamic balanced signature parsing, and a new variant of deterministic dynamic strings. We elaborate more on these techniques in the rest of the talk. We also present the following auxiliary result. The above situation, in which we can efficiently perform various updates on the text, including cut-paste operation, may leave a sense of incompleteness regarding the operation copy-paste, which appears to only be a slight variation on the cut-paste. We show that, despite this similarity, supporting this operation in the dynamic setting is most likely very costly. More precisely, we prove a conditional lower bound stating that unless the widely used online matrix vector multiplication or OMV conjecture fails, no data structure supporting suffix array or inverse suffix array queries in polylog n time can simultaneously support the copy-paste operation in O of n to 1 minus epsilon time for any epsilon greater than 0. This is a simplified version of our result. In the paper, we present a stronger version, proving that the product of runtime for the query and copy-paste cannot be bounded by O of n to 1 minus epsilon. We now take a closer look at the key ideas in our dynamic suffix array. Let awk k of p denote the set of positions p prime such that substrings of length k starting at positions p and p prime are equal. To avoid boundary cases, we state our definition using the string t infinity, which is the concatenation of infinite number of copies of t. From now on, we also assume that t ends with a unique sentinel symbol smaller than all other symbols in t. Let range beginning and range end, abbreviated rback k and rend k of p, denote the integers such that the set awk k of p is exactly the set of suffix array values in the range specified by these two indexes. Our suffix array query works as follows. We start by setting the current prefix length to 16. In lines 2-3, we compute some position j, called a witness, that matches the suffix sa of I up to the first 16 symbols, as well as the endpoints of the suffix array block containing all other such suffixes. In lines 4 through 10, we then successively narrow down the range, each time increasing the prefix length L by a factor of 2. More precisely, at the beginning of the iteration, suffix starting at position j matches the suffix sa of I up to at least L symbols, and be are the endpoints of the current range. Using this information, we first compute a new witness j prime, and then the new range boundaries b prime, e prime for length 2L. Observe that when L reaches a value greater or equal than n, the range BE is of size 1, and thus our witness j must be equal to SA of I. We thus return j as our answer in line 11. Let us take a closer look at a single step of our algorithm. To get an idea of how we compute the witness and refine the range, consider a sequence containing all positions p of the string t sorted according to the right length 2L context in t infinity, with ties resolved arbitrarily. Since in the suffix array all positions are sorted by the context of length n, the order in these two sequences is the same up to a permutation within blocks sharing a common prefix of length 2L. Therefore, if our goal is to find a witness j prime, The above order contains enough information and it suffices to take as j' the ith position in the sequence. Such j' is guaranteed to be one of the positions in the block indicated with red. This simple idea does not, however, immediately lead to an efficient data structure, since maintaining such order is not possible because a single update can change omega L contexts. For a more efficient solution, observe that in the above algorithm, we can significantly narrow down the search if we utilize the information we already have from previous step, namely the values of j and the range boundaries BE. With that additional information, to find the witness j', we only need to find the kth position among p in the above order that agree on L symbols with our witness j. This will still give us a position j' in the highlighted block of suffix array. The key benefit of this modification, compared to the initial idea, is that limiting the search to p sharing the right length L context lets us employ techniques based on local consistency. More precisely, instead of maintaining all p between 1 and n, we will only maintain positions p in some sparse subset S. Let us take a closer look at how we choose S. In 2019, we introduced the following definition. Let tau be any integer between 1 and n over 2. A subset of positions S is a tau synchronizing set of t if it satisfies the following conditions. First, whenever any two positions p and p' have equal right length 2 tau context in t, either both or neither of them are in S. This is called the consistency condition. Second, any block of tau positions in t contains no positions from S if and only if the substring of length 3 tau minus 1 starting at the beginning of that block has the shortest period smaller or equal than tau over 3. In other words, except for periodic substrings, t has to have at least one position from S in every window of size tau. This is called the density condition. The two main questions now are: first, can such S be efficiently maintained under text updates? And two, how to use S to compute a witness j' and the refined range boundaries B', E'. We start with the first question. Along with the definition of tau synchronizing sets, in 2019 we proved the following result. For any text t of length n and any tau between 1 and n over 2, there exists a tau synchronizing set S of t whose size is O of n over tau. Note that due to density condition, this is the smallest possible S we can hope for. The immediate consequence of this result is that we can construct set S that is sparse on average, since immediately from the bound on its size, it follows that the average number of positions in a length tau block is O of 1. Therefore, since by the consistency condition whether or not a position is in S depends only on the local context of length 2 tau, we obtain that an update in t causes O of 1 changes in S on average. The average bound is not, however, enough to obtain efficient worst-case updates. Hence we ask, is there a construction of S that after each update in t would require a small number of changes in the worst case? In this paper we answer this question affirmatively. More precisely, we prove that for any text t and any tau between 1 and n over 2, there exists a tau synchronizing set S of t that has essentially a constant number of positions in the worst case in every block of length tau. We call such S locally sparse. Let us move to the second question, namely how to use S to efficiently compute a witness j' and the refined range boundaries B', E'. In this talk, we make the following simplification. We assume that for every tau and every position p between 1 and n-3 tau plus 2, the shortest period of the substring of length 3 tau minus 1 starting at position p is greater than tau over 3. This way, the density condition simplifies to stating that there is at least one position from S in every window of length tau. This significantly simplifies the algorithm. The version of our paper currently on arXiv contains a fully general solution that includes the handling of the periodic case. The witness j' and the refined range boundaries B', E' are computed as follows. Let S be a tau synchronizing set of t, where tau is equal to floor of L over 3. As a reminder, we stated the consistency condition A and the density condition B. Consider the situation at the beginning of the step during our algorithm. We are given as input the boundaries BE of the suffix array interval containing suffixes that have a common prefix of length L with suffix SA of I, and j is a witness, that is, one of the positions in this block. Observe that due to our choice of tau, it holds by the consistency condition A that either none or all of the marked positions are in S, since they all share the length 2 tau right context. Suppose that they are not in S. Then we have the same situation for the following positions. Eventually, however, by the density condition B, and since 3 tau is smaller or equal than L, for some delta between 0 and tau minus 1, all positions SA of P plus delta, where P is between B and E, will be in S. This induces a partition of the right length L context of J into two strings X and Y with length of X equal to delta. With the above observation in mind, our strategy is therefore to store all positions in the set S sorted according to the right length 2L context in T infinity. Observe that given such ordering of S, we can identify the set of positions in the suffix array block from B to E by first narrowing down the range of positions from S to only contain those having the right context Y, and then leaving only those positions that are preceded by X. Selecting the kth remaining position S gives us an element of the set OC to L of SA of I plus delta. To see this, recall that positions from S in both left and right figure are sorted by right context of length at least 2L. Therefore, since we also have that S is preceded by the string X, it holds that position J' equal to S minus delta matches the suffix SA of I on a prefix of length 2L plus delta, which is greater or equal than the length 2L required for J' to be a new witness. The reason why J' is only guaranteed to be a witness and is not necessarily equal to SA of I is because the positions in the sequence on the right are only sorted by the length 2L right context, and not the full right context. Thus, they may be permuted compared to their ordering at offset delta in the suffix array interval on the left. For example, S may happen to be the second position in the sequence on the right, but third when we are considering the full right context. If that happens, as visible on the left, our witness J' will be the position right next to SA of I in the suffix array. To efficiently implement the algorithm outlined on the previous slide, we represent the set S as points, with the coordinates on one axis being their lexicographically sorted right length 2L contexts, and coordinates on the other axis being the reversed left length tau contexts. This way, the subset of positions of S we are interested in forms a 2D range. In the figure, we highlighted the string X in blue, the string Y in green, and the range we are interested in with red. As shown in the figure, our 2D range can be computed by intersecting the 1D range for the reversed string X with a line over X denoting the reverse operation, and the 1D range for string Y, where X and Y are defined as earlier. Observe that delta can be computed from J by subtracting the successor of J in S from J. Thus, all the information to determine the string X and Y, and thus the 1D ranges, is computable from the witness J. As observed earlier, to now determine the witness J', it suffices to simply select the kth smallest point in the 2D range, where k is equal to I minus b. In the figure, this corresponds to the kth highest point. The selected point yields the position S. The witness J' is then obtained by subtracting delta from S. Once we have J', we then obtain the range boundaries B', E' as follows. First, we compute the 1D interval containing all positions from the set S having the right context of length 2L minus delta matching position S. This splits the main range into three 2D subranges. The middle range then contains all positions S' from S, such that S' minus delta matches the suffix SA of I on a prefix of length 2L. By the consistency condition, these are all the positions in the set OC to L of SA of I. Thus, to compute the boundaries of the refined range, it suffices to count points in the top and bottom ranges. More precisely, this way we obtain the values B' minus B and E minus E'. From that we easily obtain B' and E', since the values B and E are known. We have shown how to reduce suffix array queries to orthogonal range selection and counting on a multiset of string pairs defined with the help of locally sparse synchronizing set, at least assuming that our text does not have periodic substrings. What remains, however, is to explain how to efficiently implement these range queries and how to construct the underlying locally sparse synchronizing set. Let us first address the dynamic range queries. To implement the queries, we use the comparison-based 2D range trees. If coordinates of points can be compared in O of t time, this data structure implements all operations including insertion, deletion, range counting, and range selection in O of t polylog time. In our case, the coordinates of points are substrings of either the string t infinity or reversed t infinity. We can thus compare them using longest common extension queries. We can therefore use the existing dynamic LCE data structures. The second problem is that of efficient construction and maintenance of dynamic string synchronizing sets. This is a very challenging problem, and hence we only mention our key technique. All prior applications of string synchronizing sets are static. As announced earlier, to enable text updates, we developed a new variant of synchronizing sets with the extra local sparsity property. To achieve that, we developed a technique we called dynamic balanced signature parsing, extending the signature parsing of Alstrup et al. This results in the first efficient algorithm for maintenance of dynamic string synchronizing sets. Due to the use of deterministic coin tossing, the synchronizing set derived from balanced signature parsing is slightly larger than the optimal one. More precisely, the price we pay is the increase in size by a factor of log star of tau times sigma. As a side result of independent interest, our construction also yields a new implementation of deterministic dynamic strings. This concludes the talk. In this paper, we presented the first dynamic suffix array with both queries and updates in polylogarithmic time. Our structure supports all standard updates such as insertion and deletion, as well as more advanced updates such as cut-paste. Moreover, we leap directly to a solution where the complexities of all operations are deterministic and worst case. To achieve our result, we propose several new techniques of independent interest. This includes locally sparse as well as dynamic string synchronizing sets, dynamic balanced signature parsing, and a new variant of deterministic dynamic strings. Finally, we also give a conditional lower bound on the hardness of the copy-paste operation. Open problems include proving further lower bounds on the queries or updates, exploring the possible time-space trade-offs, and studying whether or not it is possible to construct linear-size locally sparse synchronizing sets. Thank you for listening to this talk.